Hi, so some time ago I made this. It's actually a self-excited generator made from a washing machine motor. Now, a washing machine motor here in the UK is a universal motor. Other places you find induction motors, but here they're universal motors, which means they'll run on AC or DC. Now, I did the conversion to create a self-excited generator, and if you don't know what that is, then you didn't watch video 1363, did you? In which case, you probably need to go and watch it. But I created this thing. Now, it is one of my pet peeves to call these things generators. As a generator implies that it makes something, and of course this doesn't make anything. I could try to make it make something by yelling at it loudly. Generate! Come on, you SOB! Nothing. And of course it wouldn't be anything. And this may seem really silly, but it isn't. It's actually really important to our understanding of what generators are, because this won't do anything until I do that. When I turn that, then electricity will come out. This mysterious lump of metal is doing something. It's taking my turning and changing it into electricity. So I think these are better called converters than they are generators, because they take one form of energy, and in this case the mechanical energy I'm applying to with my hand, and it changes it into another form of energy, in this case electrical energy. So what's happening is one form of energy is being converted into another form of energy, and that's why I think we should call them converters, because we can understand that a converter needs something in order to give something out. A generator has that mystical context of something will just come out of it. And you find people talking about generators as if something will mystically come out of them, but they're completely governed by what you put in. A generator, I'm going to call them a converter. A converter is an arrangement of wires of magnets that we saw in 1363, responsible for converting basically mechanical energy into electrical energy. And like I say, that may seem quite fatuous, but that is really important, because the electrical energy doesn't sit in here like it's a big vat of water and we can turn on the tap, it'll come out. That won't happen. We need to input something, and that input is converted to an output, and that is really significant, even though it doesn't seem to be at first sight. Did you know, when a big roll of paper is changed into A4 sheets, that's chopping up the big roll, that's called conversion. It's the same idea. You'll only get as many A4 sheets out as the big roll can feed in there. When that big roll runs out, there'll be no more A4 sheets coming out. It has to have something going in, and when that thing runs out, what comes out stops coming out. So if I'm inputting energy by twiddling that there, the energy that comes out, and I'm going to adopt standard ideas, okay, standard physics, where the energy out is always going to be less than the energy in, and certainly not more than the energy in. If you disagree with that, fantastic. But let's take that as read for this moment in time for the sake of this argument about converters. So this energy that I'm putting in here mechanically with my hand, it takes me a bit of effort to do it, because there's some resistance in here and there's going to be some losses in here. So the energy that comes out in the same way as the paper can't be more than the energy I'm putting in. It must be less than or equal to. When that runs out, what comes out stops coming out, so it must be less than or equal to. We tend not to think about it as being this mysterious energy, we tend to think about it being power. So the amount of power I put in there is going to be less than or equal to the amount of power that comes out of there. Now, electrical power, we deal with it in terms of volts and amps. And amps that come out of a generator are always a huge mystery. And I think they're a mystery because I think we have the whole thing on its head. It's not the amps that come out and the volts that come out, it's the power that comes out. So I put some power in, some power must come out, that power must be less than or equal to the power that I put in. Now in 1363 we went into how voltage is generated, and it was a reasonable amount of in depth, but let's just say that the voltage at this point is generated as an electromotive force, the result of the strength of the magnetic field, the length of the wire that's in there, and the speed that it turns. That governs the voltage output. Once we've got the voltage output and we know what the power is, then the amps is going to be directly related to that. Amps aren't output there as a thing in themselves. The voltage is generated by the structure and by the speed at which it runs. The power is dictated by how much I'm twiddling that or what I'm twiddling it with. Therefore, the amps is the result of that. Now, volts times amps equals power, watts. So watts over voltage is going to be equal to amps. So if I'm putting in 1 watt in here, for example, of mechanical power, I'm going to get 1 watt or less out of there. And if I'm spinning it at a speed that delivers a volt because of the mechanical arrangement of wires and magnets that I've got in there, then the amps is going to be 1 amp. Actually less than 1 amp, because we're going to have losses. Amps aren't something that are generated all of by themselves. Amps are something that's governed by the power I put in and the structure of this in terms of the volts that it makes. Now I hope that's clear. Let's look at this bit for a second. In this bit we have to attach something to get that to turn, and it doesn't matter what we attach there. I mean, here I've attached my hand and I'm doing it, but we could put a water wheel, we could put a windmill, we could put a steam engine, we could put a petrol engine, we could put lots and lots of very small animals. Doesn't matter. What we put on there is some form of mechanical energy to turn that shaft. This arrangement, again, it doesn't really matter to the job that it does what that arrangement is. That arrangement of wires and steel and magnets converts that to electrical output. Now, the arrangement here is about efficiency, because remember, we can't get more than we put in. It's always going to be less. It's a question not of can we get more, but how much less? How much can we lose? So these arrangements are all about efficiency. They in themselves don't generate anything. What's generated is the machine or arrangement that we have on this side that's doing something. If we feed our hamsters with enough corn and put them on a wheel, they will generate mechanical motion for sure. This won't. This will just convert whatever we stick on here into electrical energy. The ability of it to convert well is the efficiency of it. The arrangement of this steel, copper and magnets will influence the efficiency. It won't do anything about the generation, because the generation actually sits here at that side of things, not in here. And that's why I dislike calling this a generator so much, because it gives us the impression that that generation occurs magically in this box, and it doesn't. It occurs here at this side of the thing. It's here where a conversion occurs. If we can convert all of the generation, which is sitting out here somewhere, then this will be 100% efficient, and all of that energy will have been changed into electrical energy. That would be brilliant. It doesn't happen, but it would be brilliant if it did. And we can play around with this as much as we like to try and get something out at this side that we can actually use, because what we're looking for is something out at this side. We want the electricity out here so that we can do 2 things with it. One of the things we want to do with it is transmit it. We need to send it somewhere, because it's as much use as a chocolate teapot sitting right there. It needs to go somewhere. The other thing we want to do is convert it back, because that electricity by itself, apart from producing a few sparks and maybe giving you a heart attack, is next to useless. It only becomes useful when we attach it to some piece of apparatus that will then do some kind of job. So if we attach it to a battery, we're attaching it to the electrodes, remember, we can store it. We attach it to a motor, then we can lift things with it. But we must have some form of apparatus to do something with the electricity that we've converted here. Otherwise, it's no use whatsoever. Okay, so granted, this may seem really simplistic and obtuse, but I can't tell you how many times I get asked, yes, but how much does it generate? And I can tell you 100%, it generates nothing. It can't generate anything, it can only sit there. It can convert something, but it can't generate anything. The generation occurs here. It's why we spend so much time looking at different designs of wind turbines, because some designs are more appropriate for some situations than in other situations. And it's a question of what's appropriate. And you stick on something appropriate, And then your converter can do the conversion. And it's why we concentrate on that and not so much on that. Again, it seems extremely obtuse. However, it's extremely simple. I've got a 10mm bolt here. I've got a 6mm nut. There's no way I'm actually going to hold anything together with that. Why? Because the nut doesn't fit. I need a 10mm nut. Those two things have to be made together in order for that to perform its function. And that's the same thing with these converters. The converter has to be appropriate as well as the capture part that you've got here, because this capture part will move in a certain way. So if it's a water wheel, well, it's going to move with a very high torque and very slow. So if you get a converter that converts best at very high speeds, you've wasted your time because your nut won't fit your bolt. What you want is a converter that's suitable for a high torque capture device. Equally, if you've got something spinning like a crazy thing, then if you have a generator that is, if you have a converter that's looking for high torque and you've got something with low torque and fast spin, well, you're just going to go nowhere. You're not going to be able to turn your converter. So you need something that's appropriate to that. So the nut must fit the bolt. Then, of course, when we get something out of there, then that equally has to be appropriate. Because if you're producing something like 200 millivolts, that is going to run jack. You can't even light an LED with that. The turn-on voltage of an LED is about 1.7 volts, something like that. Mostly you're going to be wanting a couple of volts and above, or you just can't do anything with it. You can't even store it at that kind of level. You need an appropriate out as well as an appropriate in with a converter that matches those three things. And all of the work on these converters, or if you like generators, is about that. It's about taking something to match your input device, developing it so that it matches that and gives an output that is useful to you. So that might seem particularly unhelpful and confusing in itself, because how do you know? How do you go about actually working with these converters so that you can take that appropriate input and change it to an appropriate output? Well, as we discussed in 1363, surprisingly, there are in fact only three things you can play with. And that is the strength of the magnetic field, the length of the wire that you put in the magnetic field, and the speed at which you pass it through the magnetic field. That's it. If you play with those three things, which is what's available to you in a converter, because that's how a converter basically works, then that's all you've got to play with. So if you have something that is moving slowly, then you're not going to be able to generate that much if you're using a converter that requires speed. Now normally, of course, because it's so dependent on the speed, what we do is put a gear set on here so that we give up torque for speed, and that gear set can do the matching for us. You don't really want to turn a converter slowly, because a converter turned slowly would need massive magnets. If you had massive magnets and a huge amount of wire running through there, you turned it slowly, then yeah, you're going to generate. But the cost involved in there would be crippling. So what you normally do, stick some gears on there, so that you can have a reasonable converter. It turns at a reasonable speed with a reasonable amount of magnets and a reasonable amount of copper in there. So you do something like that to create that match. So a gear system can be part of that conversion of the slow-moving capture device to an appropriate input without actually playing around with this. You don't need gears. You could use massive magnets and huge amounts of copper if cost is not an issue to you, but gears change that relationship of speed and torque to give an appropriate input, given what these things are actually like. And like we said in 1363, they are the only three things available to you to play with. Same thing on the output. And of course what you're looking for is a balance between the input and the output. Now, as talked earlier about power, and this is the really important issue, remember, the power out can be less than or equal to the power in. That's it. If I'm putting power in here of a certain value, and I have a set of windings in there moving at a certain speed to give a certain voltage, that will be the maximum output in amps. Now, of course, it's not connected to anything and running no circuit, then there is no current. And so there are no amps. It needs to be connected to something that is actually wanting those amps, and so we get a current flow. Without a load, there is no current flow, and so there's no output. That load, of course, is going to require a certain amount of amps to do a job. Now, that's not a mystery. I mean, if you have a rock that's too heavy for you to lift, you need a mate, and you give them a call, and the two of you will grunt and heave it onto the bench. If a job needs to be done that requires a lot more power, you need more power. If you can't do that, then you have to supply more power somehow. So this thing, remember, is connected to an apparatus that's going to do some kind of work. It's going to require some kind of power, and that is the amp flow that will flow. And when that amp flow flows, it's going to have an effect on this, and of course you want the input to be able to match it. That's why these things are always rated. They're rated to that. Now that amp flow is going through copper wires, and copper wires are a physical thing. So if the copper isn't thick enough and the amp flow requirement is too high, and you can input the power on there, you've got enough power going in to be able to do that job, those wires are going to burn out. So you need to match the wires to what the potential amp flow would be for the load that you're going to attach. But it won't draw any more than it can actually supply. If there isn't enough power on here, that voltage will drop to zero, you'll get nothing. You need to be applying the power here at the point at which you capture that power to get the power out here. I hope that all made sense. I'm not sure it did. Maybe it just added to the confusion. But in essence, I don't think we should think of these as generators. I think we should think of them as converters. We can arrange the voltage based on the three variables we talked in 1363. There is power going in here by some kind of capture device that then is changed to be appropriate to this, maybe through gearing. That power dictates the ability of this to deliver the amps required by the load. So that is what it's all about. I think calling it a generator creates an element of mystery about it. I think if you think of it more in terms of a converter that is governed by the three factors in 1363, that is strength of field, length of wire, and speed at which it turns, I think you'll have a much clearer understanding of how you can go about playing with these things and how these things actually perform their function. Anyway, I hope it was of interest. I sincerely hope it helped. Thank you very much for watching, and please remember to like and subscribe.